Picture this: a burst of energy so colossal, it rips through the fabric of space itself, echoing across billions of light years. That deafening silence you're hearing. It's the aftermath of a supernova, a star's final, violent farewell, or perhaps the distant tremors of two black holes colliding, warping reality in their wake. These aren't just cosmic fireworks, they're the universe's most extreme events, raw displays of power that shape everything from the atoms in our bodies to the galaxies we gaze upon. And today, we're diving headfirst into 30 of the most mind-bending, awe-inspiring facts about these celestial spectacles, events so energetic they defy imagination. Think about the last time you felt small under a sky full of stars. Now multiply that by 1 trillion, because out there, beyond the quiet glow of familiar constellations, the cosmos is anything but serene. It's a battlefield of titanic forces. Gamma-ray bursts hotter than 1,000,000 suns, quasars brighter than entire galaxies, and explosions so vast they leave scars on the fabric of spacetime itself. These aren't just distant curiosities, they're the engines that forged the elements in your bones, the forces that sculpted the universe as we know it. And yet, most of us barely grasp their scale, their violence, or their breathtaking beauty. So why does this matter to you? Because every one of these events is a piece of a puzzle, our puzzle. They're clues to how the universe began, how it evolves, and yes, how it might one day end. This isn't just a tour of cosmic destruction, it's a journey to the heart of existence. From the birth cries of neutron stars to the mysterious whispers of dark energy, we're about to uncover secrets that will leave you stunned, questions that still baffle the brightest minds, and wonders that redefine what's possible. Buckle up, you're about to witness the universe at its most extreme. Gamma-ray bursts are the universe's ultimate powerhouses, cosmic detonations so intense they outshine entire galaxies for a fleeting moment. Imagine all the energy our sun will ever produce, squeezed into just a few seconds. That's the raw, terrifying scale of these explosions. They flash across the cosmos without warning, beams of high-energy radiation slicing through the void at nearly the speed of light. And their origins even more extreme. Some erupt when massive stars, dozens of times heavier than our sun, collapse in on themselves in violent supernova. Their cores don't just fade quietly, they implode with such force that jets of gamma rays blast outward like cosmic blowtorches, capable of sterilizing planets light years away. Others spark when two ultra-dense neutron stars spiral together in a deadly dance, their collision rippling spacetime while unleashing a firestorm of radiation. What makes these bursts truly unsettling is their unpredictability. They flicker to life anywhere, anytime, a reminder that the universe is far from peaceful. Yet buried in their brilliance are clues about how heavy elements like gold and platinum are forged in these catastrophic events, scattering through space to one day become part of worlds like ours. These aren't just distant flashes, they're the universe's way of rewriting its own rules. If gamma-ray bursts are the universe's flashbulbs, hypernovas are the explosions behind the curtain, supernovas cranked up to 11. These aren't just stars dying, they're stars self-destructing with enough force to rewrite cosmic chemistry. Picture a stellar giant 50 times more massive than our sun, reaching the end of its life. Instead of a graceful fade, its core collapses so violently that the shockwave rips the star apart from within. But here's the twist, it doesn't stop there. The collapse triggers twin jets of energy screaming outward at nearly light speed, piercing the star's carcass like cosmic blowtorches. That's the birth cry of a hypernova, and it often leaves behind something even more ominous, a newborn black hole, hungrily devouring what's left of its progenitor. What sets these apart from ordinary supernovas? Scale and spectacle. A typical supernova might outshine its galaxy for weeks, but a hypernova, it can pump out more energy in seconds than our sun will emit in its entire 10 billion-year lifetime. And here's where things get eerie. Many long gamma-ray bursts, those universe-spanning death flashes we just discussed, are actually hypernovas in disguise. Their jets, aimed directly at Earth by chance, appear as fleeting beacons across the cosmos, but their true legacy isn't just destruction, it's creation. The furnaces of hypernovas forge elements like gold, platinum, and uranium, then catapult them into interstellar space at unimaginable speeds, that wedding ring on your finger. Its atoms might have been born in the heart of one of these cataclysms billions of years ago. Yet for all their fury, hypernovas are rare. In our Milky Way, one might ignite every million years or so, a sobering thought when you realize the next could happen anytime, anywhere. And while we're safe from the nearest candidates, their existence reminds us that the universe doesn't just create life gently. Sometimes it forges it in the crucible of annihilation. Quasars are the universe's ultimate lighthouses, beacons of raw energy so brilliant they make entire galaxies look dim by comparison. At their heart lies one of nature's most extreme objects, a supermassive black hole, millions or even billions of times heavier than our Sun. But unlike the silent voids we often imagine, these black holes are anything but dormant. They feast on gas, dust, and even entire stars, heating the infalling material to millions of degrees until it glows fiercely before vanishing forever across the event horizon. This isn't a slow process, it's a cosmic hurricane. As matter spirals inward at nearly light speed, friction and magnetism twist it into a searing disk so luminous that a single quasar can outshine 1,000 Milky Ways. The numbers are staggering. The brightest quasars blaze with the luminosity of 10 trillion suns, visible clear across the observable universe. Their light, often emitted when the cosmos was less than 1 billion years old, serves as a time capsule, showing us the universe in its most turbulent youth when galaxies were still taking shape. Yet quasars aren't just relics, they're sculptors. The energy they unleash can blow away surrounding gas, halting star formation in their host galaxies and effectively putting a cap on their growth. This creates a paradoxical relationship where the black hole both fuels and limits its own galaxy's destiny. Even more fascinating is what happens when their active phase ends. The dazzling core fades, leaving behind a quieter supermassive black hole like the one hiding in our own Milky Way center. That means every massive galaxy we see today might have once been a brilliant quasar, its glory days now buried in the quiet dark. For astronomers, quasars are more than just cosmic oddities, they're tools. Their light pierces through vast clouds of intergalactic gas, casting shadows that reveal the universe's hidden structure. And because they're so consistently bright, they serve as distance markers, helping us map the expansion of space itself. These blazing monsters, born in chaos, have become guideposts for understanding the cosmos at its grandest scales. Blazars take the raw power of quasars and crank it up to a whole new level by aiming their fury straight at us. Imagine a supermassive black hole, just like the ones at the heart of quasars, but with a twist. Its jets of near-light-speed particles aren't just spewing randomly into space. They're locked onto Earth like a cosmic spotlight, flooding our telescopes with some of the most intense radiation in the universe. This alignment makes blazars appear hundreds of times brighter than they would otherwise, turning them into dazzling beacons even across billions of light years. What makes these jets so extraordinary? They're not just streams of light, they're fire hoses of plasma, electrons, and other particles, accelerated to velocities so high they warp the rules of physics as we know them. As these particles slam into magnetic fields or collide with slower-moving material, they release energy across the entire electromagnetic spectrum, from radio waves to gamma rays. But here's where it gets wild. Blazars don't just shine steadily. They flicker, flare, and sometimes double in brightness within mere hours, changes so rapid they defy logic. This variability suggests the jets aren't smooth rivers of energy but turbulent, chaotic maelstroms. where knots of high-energy material crash into one another like waves in a storm. Why does all this matter? Because blazars are more than just cosmic oddities. They're natural laboratories for physics we can't recreate on Earth. Their jets act like particle accelerators, far more powerful than anything humans have built, offering clues about how matter behaves under extreme conditions. And because their light has traveled across such vast distances, studying them helps us probe the structure of the universe itself, from the distribution of intergalactic gas to the expansion of space over time. Yet for all their brilliance, blazars are also cosmic mysteries. We still don't fully understand why some supermassive black holes launch these focused jets while others don't, or what precise mechanisms cause their sudden flares. Every flicker, every burst of high-energy light is a piece of a puzzle we're still putting together, one that could rewrite our understanding of black holes, relativity, and the very nature of energy itself. If black holes are the universe's ultimate vacuum cleaners, magnetars are its most powerful electromagnets, cosmic monsters that twist the very rules of physics with their sheer magnetic might. Born from the collapsed cores of dead stars, these neutron stars pack the mass of a sun into a sphere no wider than a city. But their size isn't what makes them terrifying. It's their magnetic fields, so intense they'd erase your credit cards from halfway across the solar system. We're talking fields 1,000 trillion times stronger than Earth's, forces so powerful they can distort the shape of atoms themselves, stretching electrons into needle-thin strings. Now picture this: one sudden crack in a magnetar's crust, a starquake, and its magnetic field snaps like an overstretched rubber band. The energy released in that single tremor could outshine our sun for decades, all concentrated into a burst of X-rays and gamma rays so fierce it lights up interstellar space like a flare. These eruptions, known as giant flares, are so violent they can ionize Earth's upper atmosphere from 50,000 light-years away, roughly the distance to the other side of our galaxy. In 2004, a magnetar flare from 20,000 light-years away actually compressed our planet's magnetic field, briefly rattling satellites and disrupting radio communications worldwide. That's the kind of reach these magnetic beasts have. But the true nightmare scenario, a magnetar's star tsunami. When their magnetic fields reconfigure, they can launch waves of plasma that race across the surface at half the speed of light, triggering explosions visible across the cosmos. The most extreme of these events, called hyperflares, are so rare we've only spotted a handful in recorded history. One, detected in 2004, released more energy in 1/10 of a second than our sun emits in 150,000 years. If one happened within 10 light-years of Earth, it could strip away our ozone layer, triggering mass extinctions. Yet amid all this destruction, magnetars are also cosmic alchemists. Their magnetic fields are so strong they might be forging mysterious, strange matter, a hypothetical state where atoms collapse into a soup of quarks. Some scientists even speculate these stars could be factories for heavy elements like gold, cranking them out under pressures no lab on Earth could replicate. So while they're undeniably terrifying, magnetars are also reminders of how extreme forces shape the universe, twisting matter, bending light, and occasionally reminding us just how small we really are. When two supermassive black holes spiral toward an inevitable collision, the universe doesn't just watch, it trembles. These mergers aren't quiet affairs. They're the most energetic events since the Big Bang, unleashing more power than 1 trillion supernovas combined. Picture two gravitational giants, each weighing billions of suns, locked in a death spiral so violent it ripples the very fabric of space-time. The energy released doesn't travel as light or heat, but as gravitational waves, invisible distortions in the cosmos that stretch and squeeze everything in their path, including the space between atoms. The scale of these collisions is almost incomprehensible. As the black holes orbit one another, they lose energy with each pass, emitting gravitational waves that gradually tighten their spiral. In the final moments before merger, they can whirl around each other thousands of times per second, reaching velocities close to the speed of light. The resulting shockwave isn't a sudden burst but a crescendo, a cosmic chirp that starts faint and low before soaring to a deafening peak. When LIGO, the Laser Interferometer Gravitational Wave Observatory, detected its first black hole merger in 2015, the signal lasted just a fifth of a second, yet it carried the energy of 3 suns converted entirely into gravitational waves. Now imagine that multiplied by billions for supermassive black holes. What makes these mergers truly staggering isn't just their energy output but their aftermath. The newborn black hole recoils like a cannon, often kicked away at speeds topping 5 million miles per hour. Meanwhile, the surrounding spacetime continues to vibrate like a struck gong, ringing with quasi-normal modes, fading echoes that reveal the black hole's mass and spin. And here's the twist: these collisions don't just destroy, they create. The gravitational waves they produce can fling nearby stars clear out of their galaxies, turning them into hypervelocity rogues streaking through intergalactic space. Yet for all their violence, supermassive black hole mergers are also cosmic lighthouses, illuminating the universe's hidden structure. Their gravitational waves bend around intervening galaxies, offering astronomers a new way to map dark matter. And because they're visible across unimaginable distances, they could one day help us measure the universe's expansion rate with precision. These collisions remind us that even in the darkest corners of space, chaos and creation are forever intertwined. Deep in the heart of countless galaxies, hidden beneath swirling veils of dust and stars, lies one of the universe's most relentless power plants, the active galactic nucleus. At its core, a supermassive black hole weighing millions to billions of times our sun's mass doesn't just sit silently. It feasts gas, dust, and even entire stars spiral toward it, trapped in a gravitational dance with no exit. But here's the catch: nothing crosses the event horizon quietly. As material falls inward, it doesn't vanish instantly. Instead, it piles up in a searing, chaotic whirlpool called an accretion disk, where friction heats it to millions of degrees until it glows brighter than all the stars in the galaxy combined. This isn't just a cosmic light show, it's physics pushed to the brink. The disk's inner regions spin at nearly light speed, warping spacetime itself while churning out radiation across the spectrum. X-rays, gamma rays, radio waves, you name it. The AGN hurls it into the void with enough force to influence gas clouds thousands of light years away. Some of this energy escapes in jets, narrow beams of particles launched perpendicular to the disk at relativistic speeds. Others radiate outward, ionizing entire galaxies and beyond. The most luminous AGN, known as quasars, can outshine 1 trillion suns, their brilliance visible clear across the observable universe. But AGN aren't just celestial blowtorches, they're sculptors. The energy they release can blow away star-forming gas, effectively putting a cap on their host galaxy's growth. It's a feedback loop of cosmic proportions. The black hole's appetite fuels its brilliance, which in turn stifles the very material that feeds it. This delicate balance explains why some galaxies stop forming stars prematurely, their potential cut short by the monster at their center. Yet for all their fury, AGN are also time capsules. The light from the most distant quasars has traveled over 13 billion years to reach us, offering snapshots of the universe when it was less than 1 billion years old. By studying them, we've glimpsed the era when the first supermassive black holes were taking shape, growing impossibly fast, defying our models of how such giants could form so soon after the Big Bang. What's perhaps most humbling is the realization that our own Milky Way harbors a quiet AGN, a dormant supermassive black hole that may have once blazed as brightly as the quasars we see today. It's a reminder that even the most extreme cosmic engines can fade, leaving behind only echoes of their past fury. Yet their legacy endures, written in the distribution of galaxies, the composition of intergalactic space, and the very elements that make up our world. Our sun may seem steady from day to day, but beneath its calm surface lurks a potential for chaos. Solar flares, eruptions of energy so vast they can dwarf humanity's most destructive weapons. These explosions happen when twisted magnetic field lines on the sun's surface suddenly snap, releasing pent-up energy across the electromagnetic spectrum from radio waves to X-rays in mere minutes. The largest flares, classified as X-class, unleash energy equivalent to billions of hydrogen bombs detonating at once. Yet the real danger isn't the explosion itself, it's the aftermath. Take the Carrington event of 1859, the most powerful solar storm ever recorded. A flare so intense it set telegraph systems ablaze, sparking fires, shocking operators, and lighting up skies as far south as the Caribbean with auroras so vivid, people mistook them for dawn. Today, a storm of that magnitude would wreak havoc on a global scale. Modern power grids, satellites, and communication networks could face catastrophic failures, with cascading blackouts lasting months or even years. The economic toll, estimates suggest trillions in damages, far exceeding any natural disaster in human history. But what makes solar flares truly unsettling is their unpredictability. The sun doesn't telegraph its outbursts. We might only have minutes to prepare before a torrent of charged particles slams into Earth's magnetic field, distorting it like a punch to a giant invisible shield. These particles can induce electric currents in power lines, overloading transformers and frying delicate electronics. In 1989, a flare a third as strong as Carrington's knocked out Quebec's power grid in seconds, leaving millions in the dark during a frigid winter night. Yet for all their destructive potential, solar flares are also breathtakingly beautiful. The same particles that threaten our technology paint the skies with auroras, turning Earth's poles into canvases of shimmering green and crimson. They remind us that we're not just observers of the cosmos, we're participants, orbiting a star that's as capable of wonder as it is of fury. And as our reliance on technology grows, so does the urgency of understanding these eruptions, because the next great flare isn't a matter of if, but when. While solar flares light up the sun in bursts of radiation, coronal mass ejections are the real heavyweights, cosmic hurricanes hurling billions of tons of superheated plasma into space at speeds topping 7 million miles per hour. Picture the sun tearing off a piece of its own atmosphere and flinging it outward with enough force to cross the distance from Earth to the Moon in under 15 minutes. These aren't just clouds of gas, they're tsunamis of charged particles wrapped in tangled magnetic fields, capable of distorting planetary magnetospheres like a fist squeezing a balloon. The violence begins in the sun's corona, where unstable magnetic fields snap like overstretched rubber bands, catapulting plasma outward in a chaotic, expanding bubble. Unlike the near-instantaneous flash of a solar flare, a CME unfolds in slow motion, taking hours to fully erupt, but its effects linger for days. When one barrels toward Earth, our planet's magnetic field absorbs the blow, compressing on the sunward side while stretching into a long tail on the opposite side. The results range from dazzling to devastating. Auroras, normally confined to polar latitudes, can spill as far south as the equator, painting skies with unearthly hues. But the same electromagnetic turbulence that creates these light shows can also induce rogue currents in power grids, melt transformers, and knock satellites offline. History offers stark warnings. The 2012 near-miss CME, comparable in scale to the Carrington event, crossed Earth's orbit just 1 week after our planet had rotated out of harm's way. Had it struck, studies suggest global blackouts could have lasted years, with cascading failures crippling water supplies, refrigeration, and financial systems. Even Mars isn't immune. When a CME stripped away part of its atmosphere in 2015, it offered a chilling preview of how these storms may have contributed to the planet's desiccation over billions of years. Yet for all their destructive potential, CMEs also play a paradoxical role in shaping habitable worlds. By eroding hostile atmospheres over eons, they might have helped clear the way for life on planets like Earth. Their magnetic chaos even seeds interplanetary space with rare isotopes, some of which end up preserved in tree rings and ice cores, silent records of the sun's fury across millennia. So while we brace for the next big storm, we're also learning to read these eruptions as both threat and testament to our cosmic connection. Pulsars are the universe's metronomes, neutron stars spinning so fast and so precisely they rival the most accurate atomic clocks on Earth. Born from the explosive deaths of massive stars, these ultra-dense remnants pack more mass than our Sun into a sphere no wider than Manhattan. But what makes them extraordinary isn't just their density, it's their rhythm. As they rotate, beams of radiation shoot from their magnetic poles like cosmic lighthouse beams, sweeping across space with such regularity you could set your watch by them. Some spin hundreds of times per second, their pulses arriving with a consistency measured in nanoseconds over decades. Take the famous pulsar B1913+16, the first binary pulsar discovered. Its pulses arrive with such clockwork precision that astronomers detected tiny delays, just thousandths of a second over years, caused by gravitational waves rippling through spacetime. This observation, earning a Nobel Prize, confirmed Einstein's prediction that orbiting massive objects should radiate these invisible ripples. Pulsars became nature's relativity labs, their unwavering ticks revealing the subtle warp and weft of the cosmos. But their precision hides terrifying origins. A pulsar's spin comes from its progenitor star's collapse, like a figure skater pulling in their arms to spin faster. As the star implodes, its core, now a neutron star, conserves the original rotation, accelerating to dizzying speeds. The magnetic field, amplified during collapse to 1 trillion times Earth's strength, channels charged particles into beams so intense they can be detected across galaxies. What's perhaps most astonishing is how we use them. By tracking networks of these cosmic beacons, astronomers hope to detect the faint gravitational wave background from supermassive black hole mergers across the universe. Others serve as interstellar GPS, with proposed spacecraft using pulsar signals to navigate beyond our solar system. Even now, the faintest, oldest pulsars spinning just once every few seconds act as time capsules from the early universe, their slowed rotations telling the story of how these cosmic dynamos gradually lose energy over billions of years. Yet for all their regularity, pulsars occasionally defy expectations. Some suddenly speed up in glitches, likely from quakes in their crystalline crusts or vortices in their superfluid interiors. Others, called magnetars, erupt with enough magnetic fury to disrupt Earth's upper atmosphere from halfway across the galaxy. These exceptions remind us that beneath their precise exteriors, pulsars remain some of the most extreme and enigmatic objects in existence. Natural laboratories where matter, gravity, and magnetism push the limits of known physics. Fast radio bursts are the universe's most cryptic signals, blips of radio waves so intense they outshine entire galaxies for a fraction of a second before vanishing without a trace. First discovered in 2007, these millisecond flashes arrive from billions of light-years away, packing as much energy as 500 suns emit in an entire day. But here's the real mystery: we still don't know what creates them. Some erupt once and disappear forever, while others repeat unpredictably, like a cosmic Morse code with no discernible pattern. The leading suspect, magnetars, those ultramagnetic neutron stars we met earlier. In 2020, astronomers caught one red-handed, a magnetar in our own galaxy firing off an FRB-like signal, suggesting these exotic objects could explain at least some burst. The theory goes that when a magnetar's crust fractures under unimaginable magnetic stress, it might unleash a storm of radio waves powerful enough to cross intergalactic space. But not all FRBs fit this mold. Some repeat with erratic timing, while others appear in galaxy regions where no magnetars have been spotted. That's where wilder ideas come in. Could some FRBs be produced by advanced alien civilizations? It's a long shot, but researchers have considered the possibility, perhaps as leakage from planet-sized transmitters or even light sails propelled by focused radio beams. The truth is likely far stranger than fiction. One repeating burst, FRB 121102, pulses every 157 days like clockwork, hinting at an origin tied to orbital dynamics, maybe a neutron star wobbling around a companion star or black hole. What makes FRBs invaluable isn't just their mystery, but their utility. As these signals traverse the cosmos, they interact with the sparse electrons between galaxies, allowing scientists to measure the universe's missing matter, the invisible web of gas that makes up half the atoms in existence. Every burst is like a flashlight beam through cosmic fog, revealing structures we'd never see otherwise. Yet for all their scientific promise, FRBs remain tantalizingly elusive. New telescopes like CHIME in Canada are detecting dozens each month, but each discovery raises fresh questions. Why do some arrive with a radio twist, their waves polarized as if they've traveled through extreme magnetic fields? Could different types of FRBs come from entirely distinct cosmic phenomena? The more we find, the clearer it becomes. These fleeting signals are probing the frontiers of physics, challenging us to rethink what's possible in the universe's most energetic corners. Imagine a star not unlike our Sun, cruising peacefully through the galaxy until it strays too close to an invisible predator lurking in the darkness. In a cosmic ambush, the black hole's gravity seizes it, stretching the star like taffy in a process so violent, astronomers call it spaghettification. This is a tidal disruption event, one of the universe's most brutal displays of gravitational dominance, where a star isn't just swallowed whole but torn apart in a spectacular burst of light and energy. The carnage begins when the star crosses the black hole's tidal radius. The point where gravity's pull on the near side is so much stronger than on the far side that the star can't hold itself together. Like a rubber band stretched past its limit, it snaps. The star's outer layers are shredded into a stream of gas, spiraling toward the black hole in a swirling accretion, disk so hot it glows with the fury of a million suns. Meanwhile, the star's core, if it survives the initial stretch, might be flung away at incredible speeds, a cosmic survivor hurled into the void. But here's where it gets even wilder. The debris doesn't just vanish quietly into the black hole. As it's ripped apart, friction and magnetic forces heat the gas to temperatures exceeding hundreds of thousands of degrees, igniting a flare of X-rays and ultraviolet light so bright it can outshine the star's entire lifetime of nuclear fusion in mere months. These flares are beacons across the cosmos, betraying the presence of otherwise invisible black holes. In 2019, astronomers spotted one such event 375 million light-years away, its light curve revealing the black hole's mass about 6 million times that of our Sun, and even the unfortunate star's composition. What makes tidal disruptions more than just cosmic violence is their role as natural laboratories. The way a star's material spirals inward reveals the black hole's spin, while the light echo of the flare maps the debris disk structure in ways no simulation can replicate. Some disruptions even produce relativistic jets, narrow beams of particles shot outward at nearly light speed, hinting at how black holes power some of the universe's most energetic phenomena. Yet for all we've learned, mysteries remain. Why do some disruptions flare brightly in X-rays while others glow in visible light? Could the star's angle of approach or the black hole's spin tip the scales between total annihilation and a partial escape? Each new detection peels back another layer, showing us that even in destruction, stars have stories to tell, stories written in the light of their final, cataclysmic moments. When two neutron stars, cosmic remnants so dense a teaspoon of their material weighs more than Mount Everest, finally spiral into each other after a billion-year dance, the universe doesn't just witness a collision. It experiences a kilonova, an explosion so powerful it rewrites the laws of physics in real time. Picture this: two city-sized objects, each packing a sun's worth of mass, smashing together at nearly a third the speed of light. The impact is so violent it rips open the fabric of space-time, sending gravitational waves pulsing across the cosmos while simultaneously unleashing a firestorm of gamma rays visible across billions of light years. But the true magic happens in the aftermath. As the neutron stars merge, their crushing gravity squeezes neutrons like oranges, producing exotic nuclear reactions that forge heavy elements at breakneck speed. In mere seconds, a single kilonova can synthesize hundreds of Earth masses worth of gold, platinum, and uranium elements far too heavy to form in ordinary stars. These precious metals are then catapulted into space by the explosion's shock waves, eventually seeding future generations of stars and planets. That means the gold in your jewelry likely began its journey in a cataclysm like this, scattered across the galaxy before Earth even existed. The historic detection of GW 170817 in 2017 marked the first time astronomers caught this cosmic alchemy in action. The gravitational waves from the merger arrived at Earth first, detected by LIGO and Virgo observatories. Less than 2 seconds later, NASA Fermi telescope picked up the accompanying gamma ray, burst a flash so energetic it briefly outshone all the stars in the observable universe combined. Over the next days and weeks, telescopes worldwide watched as the kilonova's radioactive glow revealed something never before seen: the signature of freshly minted heavy elements, their spectral lines confirming theoretical predictions about how the universe's richest metals are born. What makes kilonovas more than just dazzling light shows is their dual role as cosmic messengers. Their gravitational waves let us measure the expansion rate of the universe with unprecedented precision, while their electromagnetic afterglow acts like a forensic toolkit, revealing the physics of matter under conditions we could never replicate on Earth. Some models even suggest certain kilonovas might forge stable superheavy elements beyond the periodic table's current limit, substances that could rewrite our understanding of chemistry itself. Yet for all their destructive origins, kilonovas are ultimately creators. Every such event enriches the cosmos with the building blocks of planets, technology, and even life. These collisions remind us that the universe's most violent moments often lay the groundwork for its greatest complexities, turning the ashes of dead stars into the foundations of new worlds. Dark energy is the universe's greatest unsolved riddle, an invisible force not just expanding space but stretching it apart at an ever-increasing speed. Picture blowing up a balloon with dots on its surface. Now imagine those dots racing away from each other faster and faster without any extra air being added. That's the eerie reality we're facing. In the late 1990s, astronomers studying distant supernova made a discovery that upended cosmology. Instead of slowing down as expected after the Big Bang, the universe's expansion was accelerating. Something was counteracting gravity's pull on cosmic scales, something we now call dark energy, though dark here means unknown rather than literal darkness. This mysterious pressure now makes up about 68% of the universe's total energy content, dwarfing everything we can actually see. Its effects are subtle but omnipresent, gently pushing galaxies apart over billions of years. Here's the paradox: the more space expands, the more dark energy there seems to be, creating a feedback loop that could eventually rip the cosmos apart atom by atom. One leading theory suggests dark energy might be the energy of empty space itself, what Einstein once called the cosmological constant. Quantum physics tells us a vacuum isn't truly empty. It's a seething foam of virtual particles popping in and out of existence. Maybe their fleeting energy fuels the acceleration, yet the numbers don't quite add up. Calculations predict a vacuum energy value 10 to the power of 120 times larger than what we observe, the worst mismatch in science. Alternative ideas propose dark energy might be a dynamic field, evolving over time like an invisible fifth force. Some even speculate it's linked to extra dimensions predicted by string theory. What's undeniable is the stakes. If acceleration continues unchecked, distant galaxies will eventually vanish beyond an unreachable horizon, leaving future civilizations with a night sky nearly empty of stars. Alternatively, dark energy might strengthen until it shreds galaxies, solar systems, and even atomic bonds in a big rip. Or more hopefully, it could fade, allowing gravity to pull the cosmos back together in a big crunch. Every measurement of supernova, galaxy clusters, and the cosmic microwave background brings us closer to answers, but for now, dark energy remains the universe's most consequential mystery, a reminder that the fate of everything may hinge on something we don't yet understand. Cosmic rays are nature's own particle accelerators, invisible bullets of energy screaming through space at nearly the speed of light. These aren't rays in the traditional sense. They're mostly protons and atomic nuclei, some packing enough punch to rival a fast-pitched baseball. Concentrated into a single subatomic particle, their origins read like a cosmic detective story, most likely forged in the shockwaves of supernova explosions, where turbulent magnetic fields act like massive slingshots, hurling particles across interstellar space. Others may come from active galactic nuclei, where supermassive black holes accelerate matter to energies we can't replicate even in our most powerful colliders. When these high-speed projectiles collide with Earth's atmosphere, they trigger cascades of secondary particles, a silent fireworks show happening above our heads every second. Scientists detect these air showers using arrays of sensors spread across deserts and mountaintops, watching for the faint trails of light or radiation produced when cosmic rays meet our planet's protective shield. The highest energy cosmic rays are so rare that only a few per century strike each square mile of Earth's surface, yet they carry energies millions of times greater than anything produced in human-made accelerators like the Large Hadron Collider. The mystery deepens when we trace their paths backward. While low-energy cosmic rays clearly originate within our galaxy, the most energetic ones seem to come from beyond the Milky Way. Their trajectories are scrambled by interstellar magnetic fields, making it impossible to pinpoint exact sources, though some suspects include colliding galaxy clusters or the relativistic jets of distant quasars. One ultra-high-energy particle detected in 1991, nicknamed the "Oh my God" particle, was moving so fast it would reach the moon in under 5 seconds if it weren't for relativity. Its energy was equivalent to a bowling ball dropped from head height, concentrated into a single proton. What makes cosmic rays more than just a curiosity is their role in shaping life itself. These particles constantly bombard our planet, contributing to natural background radiation and potentially influencing cloud formation and even genetic mutations over evolutionary timescales. Astronauts on the International Space Station report seeing flashes of light when high-energy cosmic rays pass through their retinas, a startling reminder that space is far from empty. Meanwhile, scientists continue hunting for cosmic ray factories using neutrino observatories buried deep in Antarctic ice, hoping these ghostly particles might lead us back to the sources of nature's most powerful projectiles. Yet for all their impact, cosmic rays remain stubbornly enigmatic. Why do their energy levels abruptly drop off above a certain threshold? Could some originate from exotic processes like decaying dark matter or cosmic strings? Every new detection adds another piece to the puzzle, revealing a universe far more dynamic and far more dangerous than we often imagine. Relativistic jets are the universe's ultimate particle cannons, narrow beams of plasma, launched from black holes and neutron stars at speeds so close to light that time itself warps for the material inside them. These aren't gentle streams but focused torrents of ionized gas, stretching tens of thousands of light years across space, piercing through galaxies like cosmic lances. The physics behind them defies intuition. Imagine a supermassive black hole, its gravity so intense that not even light can escape, yet somehow it's hurling matter outward at nearly 99.9% the speed of light. This paradox is possible because the jets don't come from the black hole itself, but from its swirling accretion disk, a maelstrom of superheated gas and twisted magnetic fields. As material spirals inward, some of it gets caught in magnetic field lines that act like cosmic railguns, channeling particles along the black hole's spin axis and accelerating them to relativistic speeds. The energy involved is staggering. A single jet from an active galaxy can outshine its host galaxy by 100 times, radiating across the electromagnetic spectrum from radio waves to gamma rays. The most powerful jets, like those from the quasar 3C273, pump out enough energy every second to power human civilization for billions of years. And they're not rare. Astronomers estimate most supermassive black holes go through phases of jet production, turning them into temporary beacons visible across the observable universe. What makes these jets especially fascinating is their structure. Despite spanning distances far larger than entire galaxies, they remain incredibly narrow, often diverging by less than a few degrees. This tight focus comes from magnetic cocoons surrounding the jet, self-reinforcing fields that prevent the plasma from dispersing into space. Some jets even exhibit knots and flares, regions where shockwaves boost particles to even higher energies, creating bright spots that flicker over years or decades. The impact of relativistic jets extends far beyond their dazzling light shows. When these beams plow into surrounding gas clouds, they trigger star formation by compressing the material, effectively turning destruction into creation. Others carve vast bubbles in intergalactic space, leaving behind radio lobes detectable billions of years later. Even our own Milky Way likely had active jets in its past, faint remnants still visible as giant bubbles of gamma rays stretching above and below the galactic plane. Yet for all their power, relativistic jets are also cosmic mysteries. Why do some black holes produce them while others stay quiet? How do particles in the jets survive acceleration without being torn apart? Every new observation peels back another layer, revealing a universe where even the darkest objects can become beacons speeding through the void, bending the laws of physics and reshaping the cosmos in their wake. The Big Bang wasn't just an explosion, it was the explosion, the ultimate energy event that birthed space, time, and everything we know in a single, incomprehensible moment. Picture all the energy in today's universe, every star, every galaxy, every flicker of light compressed into a space smaller than an atom. Then imagine it erupting outward faster than the speed of light, not into empty space, but creating space itself as it expanded. In that first fraction of a second, temperatures soared to 100 million billion degrees Celsius, so extreme that the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces were indistinguishable, fused into a single, unified power. The evidence for this cosmic genesis is etched into the sky. In 1965, astronomers Arno Penzias and Robert Wilson stumbled upon a faint, persistent hiss in their radio telescope, a whisper of microwave radiation coming uniformly from all directions. This cosmic microwave background, or CMB, is the afterglow of the Big Bang, cooled over 13.8 billion years from white-hot light to just 2.7 degrees above absolute zero. But it's more than a relic, it's a fingerprint. Tiny fluctuations in the CMB's temperature variations as subtle as 1 part in 100,000 reveal the seeds of all cosmic structure. Those microscopic wrinkles in space-time grew into the vast webs of galaxies we see today, pulled together by gravity's patient hand. What's staggering is the sheer scale of energy conversion during those first moments. As the universe expanded and cooled, its energy transformed like a cosmic alchemist's recipe. Within the first second, quarks and gluons, the building blocks of protons and neutrons, condensed out of the primordial soup. Minutes later, nuclear fusion forged the first hydrogen and helium nuclei in a process called Big Bang nucleosynthesis. Yet most of the energy didn't end up in matter at all. It became the dark energy now accelerating the universe's expansion, a reminder that the Big Bang's influence is still shaping our cosmic fate. The deeper we look, the stranger it gets. The Planck satellite's ultra-precise CMB maps suggest the universe expanded exponentially in its first sliver of a second, a theoretical blink called inflation, stretching quantum fluctuations into cosmic-sized ripples. Some theories even propose our Big Bang might be one of countless others in a multiverse, each with its own physics. But for all its mystery, one thing is clear: every atom in your body, every photon of light, every black hole spinning in the void traces back to this singularity of energy. The Big Bang wasn't just an event, it's the ongoing story of the universe, written in the language of particles, forces, and the relentless expansion of space itself. If the universe has a self-destruct button, vacuum decay might be at a theoretical doomsday scenario where the very fabric of reality unravels at light speed, erasing everything we know in an instant. Here's how this cosmic nightmare would unfold. Hidden beneath the equations of quantum field theory is a haunting possibility that what we call empty space isn't truly empty or stable. Instead, it might exist in a false vacuum, a precarious state akin to a marble resting on a hill rather than safely at the bottom of a valley. One tiny nudge, a random quantum fluctuation, a high-energy particle collision could send it tumbling downward, triggering a catastrophic phase transition. This wouldn't be an explosion in the traditional sense. Think of it more like a bubble of true vacuum forming spontaneously, its walls expanding outward at the speed of light. Within that bubble, the fundamental constants of nature, the strength of gravity, the mass of electrons, even the behavior of light, could rearrange themselves into new, alien laws. Atoms might disintegrate, chemical bonds cease to function, and the universe as we know it would literally rewrite itself into something unrecognizable. The scariest part, there'd be no warning. By the time the bubble's light reached us, the wave of destruction would already be here. The math behind this isn't science fiction. It emerges from legitimate quantum field theories, including those tied to the Higgs field. In 2012, the discovery of the Higgs boson confirmed that the field permeating our universe gives particles their mass. But some calculations suggest this field might not be in its lowest energy state. If true, our cosmos is sitting on a quantum time bomb, stable for now but vulnerable to a random, irreversible collapse. Could this happen naturally? The odds are vanishingly small, but not zero. Some theories propose that high-energy processes like cosmic ray collisions or black hole mergers might locally tip the scales. Even stranger, if vacuum decay has already happened elsewhere in the universe, its bubble could be racing toward us right now, undetectable until it arrives. Yet there's a twist. If new physics reveals our vacuum is truly stable, or if the hypothesized true vacuum state still permits life just under different rules, this apocalypse might not be as final as it seems. For now, vacuum decay remains a chilling thought experiment, one that underscores how little we truly understand about the universe's deepest underpinnings. It's a reminder that reality, for all its apparent solidity, might be far more fragile than we dare imagine. Black holes aren't the cosmic vacuum cleaners we once thought. They leak. Slowly, imperceptibly, over timescales that dwarf the age of the universe itself. Even these gravitational titans can fade away, thanks to a bizarre quantum quirk called Hawking radiation. Here's how it works. Empty space isn't truly empty. At the quantum level, particles and antiparticles constantly flicker in and out of existence, borrowing energy from the vacuum before annihilating each other and vanishing again. Normally, this happens harmlessly, but near a black hole's event horizon, the gravitational pull is so extreme that these fleeting pairs get torn apart. One particle falls in while the other escapes, robbing the black hole of a tiny bit of energy in the process. Stephen Hawking first calculated this effect in 1974, revealing that black holes aren't eternal. They slowly lose mass, emitting a faint glow of radiation in the process. The smaller the black hole, the faster it evaporates. A stellar mass black hole might take 10 to the power of 67 years to vanish, while a microscopic one could explode in a final burst of gamma rays within seconds. This isn't just theoretical, it rewrote our understanding of how black holes interact with the universe, proving they're not just sinks of information but active participants in quantum physics. What makes Hawking radiation truly mind-bending is its implications. Over time, a black hole's temperature increases as it shrinks, meaning its final moments could be a cataclysmic burst of high-energy particles. Some theories even suggest these evaporating black holes might leave behind exotic remnants, strange nuggets of compressed spacetime with properties we can't yet imagine. Yet the biggest puzzle remains the so-called information paradox. If a black hole evaporates completely, what happens to all the matter and energy it swallowed? Quantum mechanics says information can't be destroyed, but Hawking's math initially suggested otherwise, a contradiction that sparked decades of debate. Resolving this could unlock secrets about quantum gravity, the nature of spacetime, and whether the universe itself preserves a hidden record of everything that's ever fallen into a black hole. For now, Hawking radiation stands as a haunting reminder that nothing in the universe, not even the darkest, most dominant objects, escapes the strange laws of quantum physics. The cosmos doesn't just create, it recycles, turning even the most voracious monsters into faint whispers of heat, fading into the void. Neutrinos are the universe's ultimate ghost, subatomic particles so elusive they can pass through light years of lead without a single interaction. Born in the hearts of the most violent cosmic events, from supernovas to active galactic nuclei, these nearly massless phantoms carry secrets about the universe's most extreme environments, all while leaving almost no trace of their journey. When a star explodes, for instance, 99% of its energy isn't emitted as light, it's unleashed as neutrinos, a silent tsunami of particles flooding space at nearly the speed of light. A single supernova can release so many that trillions pass through your body every second during the blast, yet you'd never feel a thing. Detecting these cosmic messengers requires instruments as extreme as their origins. Take IceCube, a neutrino observatory buried deep in Antarctic ice, where scientists monitor a cubic kilometer of frozen water for the rare flashes of blue light created when a neutrino does collide with an atom. In 2013, IceCube made history by capturing the first high-energy neutrinos traced to distant astrophysical sources, particles with energies millions of times greater than those produced in particle accelerators. Some likely originated near supermassive black holes where protons are accelerated to unimaginable speeds, then smashed into photons or other matter to spawn these ghostly byproducts. What makes neutrinos invaluable isn't just their stealth, it's their honesty. Unlike light, which can be scattered or absorbed by cosmic dust, neutrinos travel in near-perfect straight lines from their sources, offering astronomers an unobstructed view back to the event itself. When supernova 1987 exploded in the Large Magellanic Cloud, detectors on Earth caught a handful of its neutrinos arriving hours before the light did, proving these particles escape the collapsing star's core faster than photons struggling through the outer layers. That early warning hinted at entirely new ways to monitor the cosmos, not with telescopes but with neutrino eyes. Yet the most tantalizing neutrinos remain those we can't yet explain. In 2022, IceCube detected one with such staggering energy that its source remains a mystery. Dubbed the Amaterasu particle after the Japanese sun goddess, it may have come from a flaring black hole or even an unknown type of cosmic accelerator. Others might be tied to dark matter decays or other phenomena beyond the standard model of physics. Every interaction, no matter how rare, is a cipher waiting to be cracked, a whisper from the universe's most chaotic corners, carried by particles that barely acknowledge the existence of matter at all. For all their subtlety, neutrinos are reshaping our understanding of cosmic violence. They're teaching us that the universe's most energetic events aren't just seen or heard. They're felt in the faintest tremors of particles that barely interact with anything, yet hold the keys to everything. Rising above the Milky Way's bustling disk like two colossal hourglasses, the Fermi bubbles stretch 50,000 light-years into intergalactic space. Twin towers of gamma-ray energy so vast they dwarf our entire galaxy. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these faint yet titanic structures glow with the afterglow of some primordial cataclysm, their origins shrouded in mystery. But one leading theory points to a dramatic eruption from our galaxy's core, where Sagittarius, a star, the Milky Way's supermassive black hole, once awoke in a violent feeding frenzy. Imagine the scene 2 million years ago as early humans walked the Earth. Our galaxy's central black hole may have devoured a massive clump of gas or even a star. The resulting explosion would have hurled twin jets of plasma outward at near light speeds, punching through the galactic halo and leaving behind these lingering bubbles of ultra-hot gas. Today, they're invisible to the naked eye, detectable only through their faint gamma-ray shimmer, a whisper of the chaos that once raged at the heart of our cosmic home. What makes these bubbles so intriguing isn't just their scale but their composition. Unlike the orderly spiral arms of the Milky Way, the Fermi bubbles are chaotic, filled with turbulent magnetic fields and particles accelerated to energies far beyond anything we can create on Earth. Some scientists speculate they might even be cocoons for cosmic rays, those high-speed atomic fragments that constantly rain down on our planet. And here's the twist: similar structures have been spotted in other galaxies, suggesting our Milky Way isn't just a peaceful spiral but a sleeping giant capable of its own eruptions. Yet the bubbles raise as many questions as they answer. Why are their edges so sharp, as if carved by an invisible blade? Could they be the remnants of multiple outbursts rather than a single event? And most hauntingly, when will our galaxy's core awaken again? For now, these silent giants hover above us, reminders that even our familiar night sky hides scars from the universe's most violent forces, echoes of a time when the Milky Way roared with the fury of a quasar. On the night of August 15, 1977, a radio telescope at Ohio State University's Big Ear Observatory picked up something extraordinary. A 72-second burst of radio waves so intense, so unnatural, that the astronomer who discovered it scrawled, "Wow." In red ink on the printout, that impulsive note gave the signal its name, but it also captured the sheer astonishment of stumbling upon what remains, nearly 5 decades later, the most compelling and frustrating hint that we might not be alone in the universe. The wow signal wasn't just loud, it was peculiar in ways that defied natural explanations. It blasted at a frequency of 1,420 MHz, a radio quiet zone where earthly interference is minimal and cosmic hydrogen emits faint whispers. The signal's intensity spiked and faded like a siren passing by, matching exactly what astronomers would expect if it came from a distant, fixed point in space as Earth rotation swept the telescope's beam across it. Yet despite exhaustive searches, it never repeated, not once in the 46 years since. No star, no comet, no known astrophysical phenomenon fits the profile. That tantalizing one-off nature is what fuels speculation. Could it have been a fleeting transmission from an alien civilization, a cosmic hello that flickered out before we could pinpoint its origin? The signal's narrow frequency range and lack of modulation resemble what we'd expect from a deliberate beacon, not the chaotic noise of a quasar or pulsar. Some theorists even suggest it might have been an interstellar probe's propulsion signature, a burst of energy from a passing vessel we'll never see again. Skeptics, of course, have alternative explanations. Maybe it was an undiscovered comet's hydrogen cloud reflecting radio noise from Earth, though none were in the right position at the time. Or perhaps it was a military satellite's rogue transmission, though no records match the event. The truth is, we'll likely never know for sure. The wow signal exists in a limbo between proof and mystery, a cosmic Rorschach test where believers see intent and skeptics see coincidence. What makes this 72-second blip so enduring isn't just its enigma, it's the hope it represents. In a universe where we've scanned millions of stars and heard only silence, the wow signal reminds us that the cosmos might still be hiding voices. And if it was alien, the implications are staggering. Somewhere out there, even briefly, another intelligence may have aimed a signal our way. Whether it was a greeting, a malfunction, or something beyond our imagination, it stands as a humbling reminder that the universe's most energetic events aren't always cataclysms. Sometimes they're whispers waiting decades for someone to listen. Dark matter might be invisible, but if certain theories are correct, it could be hiding in explosive secret particles of this mysterious substance, annihilating each other in silent bursts of energy across the cosmos. Picture two ghostly dark matter particles drifting through space, each utterly indifferent to light, electromagnetism, and ordinary matter. Yet according to some models, when they collide under the right conditions, they might annihilate in a flash of gamma rays, neutrinos, or other exotic particles we've yet to discover. These would be cosmic fireworks with no audience, unfolding in the voids between galaxies where dark matter clumps most densely, leaving only faint traces for us to decipher. The tantalizing idea hinges on what dark matter actually is. If it consists of hypothetical particles like WIMP weakly interacting massive particles, then their mutual destruction could follow rules similar to how matter and antimatter annihilate. Except here, the energy wouldn't manifest as visible light but as high-frequency radiation, slipping through telescopes undetected unless we know precisely where and how to look. Some astronomers hunt for these signals in the gamma-ray glow of dwarf galaxies, cosmic relics teeming with dark matter but little else. Others scrutinize the center of our own Milky Way, where the supermassive black hole's gravity might concentrate dark matter, increasing collision rates. Yet the challenge is profound. Even if annihilation occurs, the signals would drown in a sea of cosmic noise, gamma rays from pulsars, black holes, and supernova. It's like listening for a whisper in a hurricane. The Fermi Gamma Ray Space Telescope has glimpsed unexplained excesses of gamma rays from the galactic center, sparking debate. Could this be dark matter's faint fingerprint or just undiscovered pulsars? The answer remains as elusive as dark matter itself. What makes this phenomenon more than a theoretical curiosity is its potential to rewrite physics. Detecting annihilation products wouldn't just confirm dark matter's existence, it could reveal its nature, mass, and interactions. Some models even suggest the energy from these collisions could subtly heat interstellar gas, slowing star formation in early galaxies. Others propose that dark matter annihilation might explain anomalous cosmic ray signatures, like the positron excess detected by the MS-02 experiment aboard the International Space Station. For now, the search continues, a high-stakes game of hide and seek with the universe's most enigmatic substance. Whether dark matter annihilates or not, the quest forces us to confront how little we truly understand about the invisible scaffolding of reality, and how much energy might be crackling unseen in the darkness. Somewhere in the depths of intergalactic space, hidden behind the dense stars of our Milky Way's central bulge, lies a gravitational phantom so powerful it's tugging thousands of galaxies, including our own, toward it at 14 million miles per hour. Astronomers call it the Great Attractor, and it remains one of cosmology's most perplexing enigmas. Imagine throwing a ball straight up, only to watch it curve sideways midair as if pulled by some invisible hand. That's precisely what's happening across our galactic neighborhood on an unthinkable scale. with entire galaxy clusters streaming toward this mysterious focal point like water spiraling down a cosmic drain. When scientists first mapped these peculiar galactic motions in the 1970s, the numbers didn't add up. The Virgo supercluster, our galactic home, should have been moving randomly with the universe's expansion. Instead, everything was being dragged toward a region roughly 250 million light-years away in the constellation Centaurus, where no visible structure appeared massive enough to explain the pull. The culprit hides behind what astronomers term the zone of avoidance, an area obscured by the Milky Way's gas and dust-making observations akin to studying a mountain range through thick fog. Early X-ray surveys eventually revealed part of the answer: the Norma cluster, a dense gathering of galaxies with the mass of 1,000 Milky Ways. But here's the catch: even this behemoth accounts for less than 10% of the attraction's calculated strength. This discrepancy has led to wilder possibilities. Some theorists suggest the great attractor might be the visible tip of a far larger structure, perhaps a supercluster of superclusters, or even a filament in the cosmic web where dark matter flows converge like rivers into an invisible sea. Others speculate it could be a gravitational illusion, our local motion reflecting the pull of something even more colossal beyond it, like the Shapley supercluster located 650 million light-years away. Then there's the most mind-bending idea of all. What if it's not matter pulling us, but repulsive dark energy pushing unevenly from the opposite direction, creating the illusion of attraction? Whatever its true nature, the great attractor forces us to confront how little we grasp about the universe's large-scale architecture. It's a reminder that even as we map billions of galaxies, the cosmos still holds shadowy giants, regions where gravity's whisper shapes the fate of everything we see while remaining just beyond our sight. Most cosmic explosions flare brilliantly before vanishing forever, but fast radio bursts have a habit of breaking the rules. Among these fleeting bursts of radio waves, a rare few do something extraordinary: they repeat. Unlike their one-off counterparts, these repeating FRBs fire off multiple signals, sometimes at regular intervals, turning what should be random cosmic noise into a tantalizing pattern. Take FRB 121102, the first known repeater discovered in 2016. Instead of fading into obscurity, it erupted again and again, flaring unpredictably for months before falling silent, only to awaken years later in a storm of renewed activity. Even stranger, some repeaters exhibit rhythms, like FRB 180916, which fires every 16.35 days with clockwork precision for 4 days before going quiet for 12. These aren't just anomalies, they're cosmic conundrums that defy our understanding of how such extreme energy gets unleashed. The repeating nature of these bursts upends early theories that pinned FRBs on cataclysmic one-time events like neutron star collisions or black hole births. If a single explosion can't explain multiple signals, what cosmic engine could possibly power these recurring eruptions? Magnetars, highly magnetized neutron stars, remain prime suspects, particularly after a galactic magnetar emitted an FRB-like burst in 2020. But repeating FRBs add wrinkles to this explanation. Some exhibit energies far beyond what a typical magnetar should produce, while others repeat too regularly to match the chaotic behavior of these magnetic monsters. Alternative theories range from pulsars orbiting dense companions to bizarre quantum phenomena in the hearts of neutron stars, where starquakes might trigger periodic energy releases. A handful of astronomers even speculate about artificial origins, though natural explanations remain overwhelmingly more plausible. What makes repeating FRBs especially valuable is their predictability. Unlike single bursts that vanish before telescopes can pinpoint them, repeaters allow astronomers to revisit their locations with deeper observations. Some appear nestled in galaxy arms rich with star formation, hinting at a connection to young, massive stellar remnants, others originate near galactic centers, suggesting supermassive black holes might play a role in energizing them. The most perplexing cases show no obvious host galaxy at all, floating in seemingly empty intergalactic space, a mystery that raises questions about whether they're flung from distant galaxies or born in environments we've yet to understand. Yet for all their mystery, repeating FRBs are more than just puzzles, they're tools. Their signals traverse vast cosmic distances, passing through clouds of ionized gas that subtly alter the burst's properties. By analyzing these changes, astronomers can map the otherwise invisible matter strewn between galaxies, piecing together the universe's large-scale structure. Some repeaters even exhibit scattering, where their signals smear slightly, revealing turbulent magnetic fields in intergalactic space. And because their repetition allows precise localization, they serve as cosmic yardsticks, helping measure the expansion rate of the universe with newfound precision. The true significance of these repeating enigmas lies in what they force us to reconsider. Nature rarely operates on human timescales, yet here we have phenomena that wink at us with eerie regularity, as if deliberately courting our curiosity. Whether they're magnetars pushed to extremes, cosmic string vibrations, or something entirely undiscovered, each repeating burst is a reminder that the universe still holds phenomena we can't yet explain, phenomena that might rewrite astrophysics when we finally decode their rhythms. Deep in the Ophiuchus constellation, nearly 400 million light-years away, a black hole committed what might be the most catastrophic act of violence ever recorded in the universe. This wasn't just an eruption, it was a cosmic detonation so vast it carved a crater in the surrounding galaxy cluster large enough to fit 15 Milky Ways side by side. The energy released 5 times greater than the previous record holder, with shockwaves rippling across the cosmos for millions of light-years. This monstrous explosion originated from the heart of a supermassive black hole within the Ophiuchus supercluster, a sprawling metropolis of galaxies bound together by gravity. Unlike typical black hole outbursts, which eject material in narrow jets, this event was a full-blown, omnidirectional catastrophe, a supersonic blast powerful enough to rip apart the surrounding intergalactic gas like tissue paper. The cavity it left behind is so enormous, it took astronomers years to recognize it for what it was. Not a random void, but the scar of an eruption so energetic. Its power rivals the combined output of every star in the observable universe, shining simultaneously for over 240 million years. How could something so colossal go unnoticed for so long? The answer lies in its stealth. Unlike a supernova or quasar, which floods space with visible light, this eruption primarily released its energy in the form of low-frequency radio waves and X-rays. Invisible to most telescopes until advanced instruments like NASA Chandra X-ray Observatory and Europe's LOFAR radio array pieced together the evidence. The faint radio glow revealed gargantuan lobes of energized particles, remnants of the initial explosion, while X-ray maps showed the gaping hole in the supercluster's hot gas where the blast had literally punched through reality. What's most baffling isn't the scale of destruction, but the black hole's appetite leading up to it. To unleash such energy, the black hole would have needed to devour staggering amounts of matter, possibly thousands of stars' worth, in a single feeding frenzy. Yet there's no visible trace of what triggered this apocalyptic binge. Some theories suggest a rare, direct collision with another supermassive black hole, or perhaps the sudden collapse of an entire molecular cloud into its maw. The Ophiuchus eruption forces us to rethink the extremes of cosmic violence. It proves that black holes aren't just passive traps for light. They're engines of chaos capable of reshaping entire galaxy clusters in moments. And lurking behind this revelation is an unsettling question. If such an event happened once, could it happen again, even in our own cosmic backyard? If black holes are the universe's ultimate drains, swallowing matter and light beyond any hope of escape, then white holes would be their cosmic opposites, theoretical fountains gushing energy and matter outward in an unstoppable torrent. These bizarre objects emerge from the same equations that predict black holes, but with time running backward. Where a black hole's event horizon marks a point of no return, a white hole's boundary would be a point of no entry, violently repelling anything that dares approach. Picture a black hole's singularity exploding like a geyser, ejecting everything it ever consumed back into the universe in a dazzling burst of energy. The math allowing white holes comes straight from Einstein's general relativity, where the equations work symmetrically in time. If a black hole is a one-way street into gravitational oblivion, a white hole would be that street reversed, with matter erupting from a singularity like a cosmic replay in reverse. Some theories even suggest white holes could be the other end of black holes connected via wormholes, though this remains speculative. The catch: while black holes form naturally from collapsing stars, white holes would require impossibly precise conditions to exist. They'd need to emerge fully formed, already packed with matter to expel, since nothing could fall in to fuel them. Intriguingly, certain fleeting cosmic events hint at phenomena that resemble white holes. Gamma-ray bursts, for instance, unleash energy comparable to what a white hole's eruption might produce. Some physicists speculate that the Big Bang itself could be viewed as the ultimate white hole, a singular eruption of all space-time and matter. Others propose that tiny primordial white holes, relics of the early universe's extreme density, might still linger undetected, occasionally burping radiation as they evaporate. Yet white holes remain firmly in the realm of theory. No observational evidence confirms their existence, and many scientists argue that thermodynamics and quantum effects would prevent them from forming naturally. But as gravitational wave astronomy advances, who knows, the universe has surprised us before. If white holes are real, they'd redefine not just how we view gravity, but the very arrow of time itself, showing us that even spacetime's rules might have loopholes waiting to be uncovered. In the vast expanse of the cosmos, where galaxies cluster like cities and cosmic filaments weave a web of matter, there exists a place so eerily empty it defies explanation: the Eridanus supervoid. This cosmic desert stretches over 1 billion light-years across, a staggering void where galaxies are suspiciously scarce, and the very fabric of space feels colder than it should. At first glance, it might seem like just another patch of emptiness in an already sparse universe, but this region holds a peculiar fingerprint, a chilling anomaly in the cosmic microwave background, the afterglow of the Big Bang, where temperatures dip unexpectedly low. Scientists call it the cold spot, and it's one of the most tantalizing mysteries in modern cosmology. The coldness of this spot isn't just a minor fluctuation. Measurements show it's significantly colder than standard models predict, as if a vast cosmic freezer lurks in that direction. One leading theory suggests the Eridanus supervoid might be responsible, a region so devoid of matter that photons traveling through it lose energy as the universe expands, cooling the light that eventually reaches us. It's like a hill in space-time. Light climbing out of this void arrives weaker and redder, leaving a cold imprint on the microwave sky. But there's a problem. The void's size and depth don't fully account for the temperature drop. The math doesn't add up, leaving researchers to wonder if something even stranger is at play. That's where exotic physics enters the picture. Some theorists propose the cold spot could be evidence of a collision with another universe, a multiverse imprint left by a long-ago brush with a neighboring bubble of reality. Others speculate it might hint at flaws in our understanding of dark energy or even the nature of gravity itself. Then there's the most unsettling possibility. What if the cold spot isn't a void at all, but a shadow cast by an incomprehensibly vast cosmic structure? Something so massive it warps spacetime in ways we've yet to comprehend. What makes this mystery so compelling is that it forces us to question fundamental assumptions about the universe. The cosmic microwave background is supposed to be the ultimate fingerprint of the Big Bang, a near-uniform tapestry of tiny fluctuations that seeded all structure. Yet here, in this one patch of sky, the pattern breaks. Whether the answer lies in undiscovered physics, statistical flukes, or something entirely unforeseen, the Eridanus supervoid stands as a humbling reminder that the universe still holds puzzles even our boldest theories can't yet solve. Amid the glittering tapestry of galaxies, filaments, and superclusters that define our universe's large-scale structure, there exists a place so empty it defies comprehension, the Boötes void. Stretching 330 million light-years across, this cosmic desert is one of the largest known voids in existence, a sphere of near-nothingness so vast you could fit thousands of Milky Ways end to end within it and still find yourself surrounded by void. For comparison, our local galactic neighborhood spans just 100 million light-years, meaning this abyss could swallow our entire cosmic region 3 times over with room to spare. Yet within its bounds, astronomers have counted only 60 galaxies, a number so pitifully small it's like finding a single grain of sand in an Olympic-sized swimming pool. The existence of such a void shakes our understanding of cosmic evolution. According to standard models, matter after the Big Bang should have clumped relatively evenly, leaving no room for gaps this enormous. Yet the Boötes void isn't just a fluke, it's a glaring anomaly. Some theories suggest it might be the result of multiple smaller voids merging over billions of years, like soap bubbles combining into one colossal emptiness. Others propose that dark energy, the mysterious force accelerating the universe's expansion, might have stretched this region thin earlier or more aggressively than elsewhere. Then there's the spine-tingling possibility that the void isn't truly empty at all, but filled with something we can't yet detect. Dark matter so cold it evades our instruments or exotic particles that don't interact with light. What makes the Boötes void even stranger is how its few galaxies behave. Instead of being evenly scattered, they cluster along faint, thread-like structures, as if huddling together for warmth in an otherwise desolate expanse. These isolated galaxies show peculiar traits too. Some are red and dead, aging prematurely with no new star formation, while others flicker with unexpected activity, as if the void itself somehow alters their life cycles. The most famous resident, the dimly glowing galaxy MCG plus 0102-015, is so alone that if you were born on one of its planets, your night sky would be almost entirely black, with no neighboring galaxies visible to the naked eye. It's the ultimate cosmic isolation chamber, yet the void's emptiness isn't just a curiosity, it's a tool. By studying how light from distant quasars passes through this region, astronomers can map the distribution of the faint intergalactic medium, the wispy gas that might hold clues to the universe's missing baryonic matter. The void's sheer size also distorts our view of the cosmos beyond it, bending light like a funhouse mirror and forcing scientists to account for its gravitational lensing effects when studying objects behind it. Perhaps the most humbling thought is that the Boötes void might not be unique. New surveys suggest other comparable voids could lurk undetected, hidden behind the Milky Way's dusty disk or camouflaged by their own emptiness. If so, our universe's structure might be far more Swiss cheese-like than we ever imagined, a labyrinth of emptiness where galaxies are the exception, not the rule. The Boötes void stands as a silent challenge to our cosmic arrogance, reminding us that for all our mapping and theorizing, the universe still holds expanses so barren they redefine the meaning of nothingness. The universe thrums with energy today. Supernovas explode, black holes collide, and stars blaze with nuclear fury. But this cosmic fireworks show has an expiration date, a far future where the last embers of energy fade into perfect stillness. This isn't just an ending, it's the ultimate victory of entropy, a state physicists call the heat death of the universe. Picture a cup of coffee left untouched on a table. At first, it's steaming, swirling with heat, but over time, that warmth dissipates until it matches the room's temperature. Now imagine that process playing out across every galaxy, every star, every atom in existence. The driving force behind this chilling fate is the second law of thermodynamics. Entropy, or disorder, always increases in a closed system. Right now, the universe is a battleground between gravity's clumping power and entropy's relentless push toward equilibrium. Stars burn because they're hot, dense pockets of hydrogen fighting against the cosmic tendency toward dispersal. But those pockets are finite. Over trillions of years, the last stars will exhaust their fuel. Black holes will evaporate via Hawking radiation, and even the protons composing matter itself may decay. What remains will be a thin, lukewarm soup of particles spread so evenly that no corner of the universe is warmer or denser than any other. No more stars igniting, no more galaxies spinning. Just an endless, featureless sea of photons and subatomic debris, all at the same temperature, a few degrees above absolute zero. Some models suggest this sterile endgame could arrive in 10 to the power of 100 years, a time span so vast it makes the current age of the universe seem like a fleeting blink. By then, the cosmos will have transformed beyond recognition. Dark energy will have pushed all remaining matter so far apart that no two particles can interact again. Even the once mighty supermassive black holes, having slowly leaked away their mass as Hawking radiation, will vanish in feeble puffs of energy. The universe won't so much end as fade into a permanent, unchangeable stasis, where the very concept of events becomes meaningless because nothing can ever happen again. Yet this grim prognosis isn't certain. Some theories hint at loopholes, quantum fluctuations that might spawn new universes in the far future, or exotic forms of matter that could reignite cosmic activity. Others propose that the heat death might not be absolute. In an infinite universe, random fluctuations could theoretically resurrect complexity given enough time. But these are speculations. What's undeniable is that heat death represents the ultimate triumph of physics over chaos, a reminder that all energy gradients, the differences that power everything from supernovas to human thought, are temporary. The universe began in a blaze of concentrated energy, and it will end in the quietest way imaginable. Not with a bang, not even with a whimper, but with the endless, unbroken hush of equilibrium. From gamma-ray bursts hotter than 1,000,000 suns to black holes colliding with the force of 1,000,000,000,000 supernovas, we've journeyed through 30 of the universe's most mind-shattering energy events, each one a testament to the raw, untamed power sculpting the cosmos. Think about that for a moment. Every atom in your body was forged in these cosmic cataclysms, stitched together from stardust scattered by explosions older than Earth itself. The universe doesn't just create, it obliterates, twists, and reinvents, with energy scales so vast they render human imagination insignificant. Take magnetars, those neutron stars with magnetic fields strong enough to distort atoms from light years away, or quasars blazing brighter than entire galaxies as they devour matter near the speed of light. Even the empty voids between galaxies, like the chilling Boötes void, whisper secrets about dark energy's grip on spacetime, and who could forget the wow signal, that eerie 72-second radio burst that still taunts us with the possibility we're not alone. These aren't just facts, they're invitations to marvel at a reality far stranger than fiction. But here's the thing, for every mystery we've uncovered, 100 more lurk in the dark. Dark matter's invisible web, the true nature of vacuum decay, the origins of those enigmatic fast radio bursts, they're all cosmic puzzles waiting for their Einsteins. That's the beauty of astronomy. The more we learn, the vaster the unknown becomes. So tell me, which of these 30 facts left you breathless? Was it the kilonova that sprinkled gold across the cosmos, or the supermassive black hole eruption that carved a crater for 15 Milky Ways? Drop your favorite in the comments, and if this journey through the universe's extremes left you craving more, hit subscribe. Because the cosmos isn't done surprising us, and neither are we every week. We'll dive deeper into the wonders and horrors lurking beyond our pale blue dot. Until then, keep looking up. The universe has plenty more fireworks in store.